Hi, I'm Sachin Kheterpal, an anesthesiologist here at the University of Michigan. And I'll be giving you a quick update on some options where big data and perioperative medicine and anesthesiology could actually be advancing some of our care. And I think the big concept here is how do we go from just the theory of big data to actually seeing it impact either our clinical operations, administrative work, or science. From a disclosures perspective, I have no relationships with any vendor on a personal level, no consulting relationship. I don't work for anybody. I do have several grants that I am PI or co-I on through my institution, where my organization, University of Michigan, receives funds from the NIH, Blue Cross Blue Shield, Merck, Edwards, Becton Dickinson, and Apple. So when we start talking about big data, it's kind of a popular buzzword. The term irrational exuberance was used by Alan Greenspan, who was the Fed chairman about 30 years ago when the first dot-com bubble was about to burst. The term just came out again recently, referring back to him. And oftentimes you see big data as just being a phrase thrown around that doesn't actually apply to any particular effort, but it's just a rebranding of existing efforts. So it's really careful what we call big data and not just thinking something is good or bad because the moniker big data is applied to it. And we also have to think about what kind of data we're trying to integrate to get big. If what you're trying to do is have a lot of perspective, meaning understanding the context of your particular patient, your particular hospital in a larger set, then you need to get data across systems, whether it's healthcare systems, different vendors, things like that all together. If you're trying to really learn the underlying biology or mechanism of action of a particular process, whether it's a biological process or an automation process, you really need to integrate different data streams. So we really have to figure out what's the purpose of your big data work, meaning is it about getting lots of data on lots of different people or really, really deep data on a smaller number of individuals to do a biological understanding. So that changes how big data is defined. Is it big in terms of the number of people involved or big in terms of the number of data points regarding a few specific individuals? And one major problem is that getting people to share their data remains tough, even with a lot of incentives out there to do collaborative science. Even though there's lots of efforts to do big data analytics, companies have to buy data streams. Even Google had to buy a traffic reporting company called Waze to integrate it into the world, even though they have more data than potentially anybody else out there. So as we think about big data perioperative medicine, I'd like to consider two concepts. On the left side, you see what I would call multi-center broad big data efforts and big data sources. And there's three major groups, what I would call well-established clinical registries that are typically manually curated. A nurse or a clinician is manually abstracting that data. Those are typically through the surgical registries. This is probably some of the best examples. The American Heart Association has something called the Get With the Guidelines, which is also oftentimes used in perioperative medicine. But NSQIP, STS are two very well-established registries there. There's a lot of administrative databases. Some of them all of them require some type of fee or purchase. Some of them are part of the federal government, like Medicare. The CMS is willing to share their data, particularly if you've got a grant from the NIH. Or AHRQ, but you can also buy data from MarketScan, Premier, Optum. Optum is the data and analytics arm of United Healthcare Group. And then what I call are some of the newer concepts, which is multi-center clinical databases, which are available, such as the Multicenter Perioperative Outcomes Group, which I lead, NACOR, the National Anesthesia Clinical Outcomes Registry, which is sponsored by the AFA. And then Optum also has some clinical data as well that they've purchased through some EHR relationships, electronic health record relationships. On the right side, you see the concept of big data defined as single center. It doesn't have to be single center, but the basic concept there is rather than patients involved, it's about depth on those patients. So it's about really deep phenotyping across CT scans, MRIs, EKGs, clinical data from electronic health record, sequencing data from the genome, potentially RNA, waveforms. These types of big data databases are around establishing new hypotheses, new biological mechanisms, and really are driven mostly by leading academic medical centers across the country and world that have done this work. And here are just a few examples of some centers that I've personally worked with that really have demonstrated some leadership related to bringing those data streams together at a very meaningful level across not just perioperative medicine, but across different specialties as well. And what they're able to do is really understand biology in a way that requires deep phenotyping. There's a couple success stories when it comes to big data and machine learning in specific. Image recognition and traffic routing are the two that I use most commonly to help understand this concept. So if any of you use Google Photos or Apple Photos, you know, it's amazing how you can actually look through your entire photo library by looking for a particular person that software has already identified. So I can look for a picture of one of my kids by just tapping on a picture of one of my kids, and it'll find all the pictures that include them. I can type in something like birthday, and it'll find all pictures that look like a birthday is occurring. And they figure that out by the fact that there's a cake and some candles and smiling people around there. And these are all algorithms that are actually very, very effective. I have to give up some privacy in order to get some of these features, but they do work and they do make your life easier. Another example is something as simple as Google Maps. The concept that thousands of people with a phone in their pocket traveling at a particular speed can inform not only what the traffic is like, but how long it would take somebody else to traverse that same pathway. That's an example of big data where we essentially sourced thousands and thousands of people going through a particular pathway and brought that up. And the reality is that this is very useful and very usable. The neat thing about this is to notice that it doesn't just give me a single pathway from LA Airport up to Santa Monica, for example. It gives me multiple options, and it lets me choose what the final correct answer is. And that's one really important concept in big data, is appreciating the lack of certainty in the final answer and communicating that lack of certainty transparently. And if you think about big data and its application in healthcare, we failed in many ways because we don't transmit and communicate that uncertainty and that humility effectively. If you look at these success stories, whether it's image recognition or traffic, you know, they don't need a lot of different data streams. In the case of pictures, they just need lots of pictures, lots and lots of pictures. And in the case of traffic, they just need your phone and your GPS to be turned on your phone, and they can figure everything else out from there. Very importantly, machine learning, big data analytics really are most useful when there's lots of features in the data that need to be considered. And when the outcome variable, meaning what you're actually trying to predict or analyze, is actually easily obtained. In the case of pictures, they just tag pictures, and they pay someone to go through and tag sample pictures as a birthday or not. They may not be your pictures, but they've tagged freely available, publicly available pictures, and then take that algorithm and apply it to your pictures. And typically, the problem is worth solving, and people want it to be solved is another key criteria. And as you see in the nice, you know, visualization of a map and the traffic route, it takes a complex concept and really makes it a nice, easy visualization. Sometimes, however, when we try and apply these concepts in healthcare, we really fail. And probably one of the biggest examples of that is IBM Watson, which is touted as being able to solve cancer, and you know, tens of millions of dollars were spent at MD Anderson and other organizations to try and solve cancer by partnering at IBM. They really failed because they overpromised and underdelivered. And even though part of my professional role is working in precision health and precision medicine, oftentimes the same can be applied to precision medicine. And why is it that sequencing people hasn't solved more healthcare problems at this, sequencing people's DNA hasn't solved more problems at this point? And it's largely because they failed to adhere to some of those critical success factors that I mentioned on the previous page. And essentially, healthcare is harder because people prefer healthcare mistakes to be made by a person. They'd rather have a doctor say, I'm sorry, I made the wrong choice there, than, oh, a device failed. And transparency is really important to both the doctor who's using that new big data algorithm and to the patient who's receiving it. And data integration is a major challenge when it comes to this concept in terms of predicting healthcare outcomes and categorizing outcomes. You have to integrate, even if you're integrating just electronic health records, you have multiple EHR vendors in most hospitals, or certainly the same EHR vendor across multiple hospitals. That's slightly different nuances. And we're generally pretty slow in healthcare to adapt and adopt new techniques, whether it's a new scientific technique or a new clinical technique. We're awfully slow in many situations. So I'll mention one group, MPOG, that I'm involved in and helped found more than a decade ago now. Basically, what we started out with was the concept that if we shared our data across academic and private hospitals, we could maybe create new insights into how perioperative patients do. So each month, each hospital, we're up to more than 50 hospitals and more than 13 million patients in our database now. They take their data from their EHR, make that data look similar across the different EHRs and hospitals, and they transmit those de-identified cases to our centralized repository at the University of Michigan. We now have, as I mentioned, about 50 hospitals, a large cluster of them in the state of Michigan due to some Blue Cross Blue Shield of Michigan sponsorship, but lots of major academic medical centers across the country and on both coasts contribute their data and gain access to the multi-center data set for research and quality improvement purposes. We have a data quality obsession, which I think is really important when you think about big data and what it can and can't do. We don't often enough think about big data's value only in the context of big data quality. If you've got bad data underneath it, it really doesn't help to do really fancy analytics. So we're obsessed with giving data quality feedback, and people have to attest to their data quality before they submit it. And so what we essentially do as part of our mission is to do research by where we don't see real-world evidence to guide practice. We actually write the papers ranging from pediatrics to OB to airway, even health services research. And then we, on the quality side of our business, which Dr. Anders, Megan Anders will be speaking regarding, we actually give that feedback on the quality side to individual providers to see how they're doing compared to colleagues at their organization and then benchmark them across different organizations as well. At this point, we're giving information back to about 4,000 providers every single month on their performance on a range of clinical performance metrics. One problem that we had when we were doing some of this work is actually trying to figure out, and as a big data example is, some of our quality metrics, for example, hypotension or how often you check blood pressure, don't apply to all cases. So we've got obstetric labor delivery cases, and so if you're at a labor epidural end, you don't have to check the patient's blood pressure every 5 minutes. So how do you figure out which cases were a C-section, which cases were a labor epidural? One way is to look at the billing code, because there's nice clean billing code, 01967 for labor epidural, 0191968 for the C-section, but oftentimes those billing codes don't show up at the database quickly enough because there's some delay there, and our providers want their feedback right away. So what should we do? How do we exclude those labor epidurals? Do we do a text search? It turns out in one other research project, we did a text search to try and find all the C-sections versus L&D, and these are all the different ways you can misspell cesarean, and it's really kind of depressing. All the different ways you can misspell delivery. There's a number 8 in that one. This one's got an E and an I. That one's got an I and an E. It's really kind of scary what happens when people type into a computer. So we said, you know what, that's not going to scale overall for hundreds of different procedures that we need to do quality improvement on. So we took 13 million cases, most of which already had a CPT code assigned retrospectively as a result of our MPOG data work, and said, let's use some basic text searching, natural language processing, and evaluate a couple different machine learning models to see which is there possible for us to tell which CPT code we will eventually see based upon the text of the procedure description. And it's not that we want the CPT code for billing purposes, we just need it to be able to categorize our research and quality improvement work. We did it in R, an open source statistical toolkit, and it showed that we can have above 90% accuracy when we use this tool. This is actually a paper that we just published a few months ago, Mike Burns and my colleagues, and he showed that for if you look at all cases, we have an average of about 88% accuracy. So based upon just the text of the procedure description, we can figure out which CPT code will eventually be assigned to that by a human coder. And for many operations, we have greater than 90% accuracy. For about half of the operations in the database, we have 90% accuracy in predicting the correct CPT code and classifying the correct CPT code, which has some quality improvement value and has some research value as well, and certainly has some financial value if you think about saving coding costs. A more clinically meaningful example of big data analytics, and this is one where you talk about big data phenotyping, is machine learning to actually predict intraoperative hypotension. This is some really nice work done out at UCLA with Edwards and Maxime Canison. They essentially said, can we predict hypotension with enough warning to predict it? And they looked at the definition of hypotension is a single minute of blood pressure below 65, mean arterial pressure below 65, and they looked at the arterial line. They had a bunch of different databases with a training database, an external validation database, and they essentially said this waveform that we get from our arterial line isn't just a single number. As it turns out, if you take all the different features of this graphical thing called an A line, it's actually 2.6 million different features with every single beat of the heart. That's perfect for machine learning and big data analytics because it requires complex, millions of features, but it also requires a lot of patience with a lot of outcomes to actually be able to dissect which features are important. And what they're able to do is come up with something called the hypoperfusion index, which is at the bottom you see the HPI, and at the top you see a patient's mean arterial pressure, much like you would during an intraoperative anesthetic record. And as you can imagine, this entire period right here on the left, the left two-thirds, the patient's mean arterial pressure is normal. It's a little bit lower, than it was at the beginning of the case, but it's pretty much normal. And I could not predict that hypotension that you see in the far right. However, the HPI, the hypoperfusion index, pretty quickly was able to detect impending hypotension defined as a mean arterial pressure below 65. And this HPI range shows that if you're in a high confidence range, as you go to the right, which is HPI telling you, a dimensionless number of between 80 and 100, that it's actually turning out there will be a high likelihood of hypoperfusion and hypotension itself. And essentially, every single time you're in the OR, you're making different choices. There's different forks in the road. And so another example of that we did with big data analytics is just provide context. So, I do some relatively uncommon surgeries. I'm a liver transplant anesthesiologist, and oftentimes there's no great clinical standard on what I should do, but I'd love to know what somebody else did in a similar situation. So wouldn't it be nice if I could get a digital consult for my anesthetic, not just for a rare one like liver transplant, but for even more common things? So what should I be using? When I'm doing a more common operation, I have a lot of anesthetic choices. I have a lot of ways to manage their pain. And essentially with 13 million cases in our database, we've got a lot of different pathways that people have taken, and somebody's probably dealt with a pretty similar patient. So we built this thing called ProView, which is essentially a patient's like mind concept. The far left, you see invasive monitoring. In the middle, you see whether or not they get a nerve block. The right here, you see what the anesthetic technique was. And over here, you see what are the different types of other medications that the patient got. And as you can see, just by the colors, a liver transplant does not have a lot of variation. These are the number of different options that people have taken. And on the far right, you see outcomes by different pathways. If you take a look at a knee replacement, you see lots of different options out there, lots of different pathways, and lots of different outcomes to consider. So I can actually pick, hey, if I went down the pathway of a 88-year-old with bad coronary disease without an arterial line with a general anesthetic, how often do they wind up needing epinephrine? Because that's what I'm worried about, is that I'll be giving epi to someone and not having an A line in place or something like that. So we can take a look at all the different pathways people have been through using big data analytics as well. And you'll notice we're really focused on visualizations as opposed to pop-up alerts. So just like that previous slide, this is something on the left called Alert Watch. My chairman emeritus, Dr. Tremper, built a company out of this where we actually can integrate data across patients to understand whether or not that patient is doing well. So I can, using big data analytics, essentially have rules built in to say if I bring lots of data regarding a patient together from their lab values, their H&T, real-time waveform monitoring, it helps me understand is the patient health status good, which is green, somewhat dangerous, which is orange, or bad, which is red. And on the right side, you see an ambulatory care example of the same concept with cardiovascular health scores. So in summary, when we think about big data and data analytics, we really need to think about the training data set really carefully. You're trying to do introspection or perspective. If you're trying to understand the biology process, that's introspection. That's maybe single center data, not multi-center big data. You have to pick solvable problems that are worth solving and that you have the right data for, and be really transparent, knowing that no technique is a panacea. Just because you happen to like a particular form of analytics doesn't mean it's going to work. And then be really humble about the limitations of the work that you do. I'll go ahead and stop there and join Megan and Mark in the Q&A session now.